Okay, let's go ahead and get started with this one. With this first one, what's an explanation as to why atoms would become ions? Okay, so that's what it means. So if you lose, okay, or gain electrons to become stable. And that stability is found where? When do they become stable?
Satisfied.
Okay, do we have an easier way to say that?
Valence level is filled with electrons.
Easier?
Like noble gases.
They look like noble gases. That's it. When their electron configurations look like the configurations of the closest noble gas, they're done reacting. Why? What do you know about the noble gases don't react? That's it. And they don't react because they don't have any electrons to react with. Okay. So so they're trying to match the noble gas configuration, the closest noble gas configuration. So how about this next one about being able to react?
Yes and no.
Say no?
I say yes and.
There's the answer right there, yes and no. The no answer is it doesn't react unless you do something to it by inputting energy. It can't react unless you add energy to it. So if you take anybody from that group 1 column and you drop them into water, it explodes, right? But after I've taken that sodium and it's lost its electron, can I take that sodium ion and put it in water and have it do something? No. But I could use like some kind of electricity and shove the electron back on it, and that thing is chemically reacting. So no unless what? Unless energy is added. So that example, I think, I'm just gonna take a guess here, but I'm guessing every single one of you did that last night. Maybe not, but probably. What am I referring to?
Cell phone?
Your cell phone. Was your cell phone charged this morning?
Yeah.
Okay. It was charged because you did the no part. You added the electricity to it to get the electrons to go back onto the lithium. That wouldn't have happened unless you plugged it in and added energy to it. Which atom is more likely to gain electrons, the silicon or the bromine? Okay. So how do I look at the table and recognize that easily?
Real quick on the previous one.
Sure.
What is the yes and no?
It's no unless you add energy, then it's yes.
Oh, I see. Okay.
So the bromine and the silicon?
Bromine has more electronegativity.
Yeah. The easiest way, an easy way would be to just look at the electronegativity number off. But what if you didn't have that, just had a table?
It's closest to a noble gas.
It's in the halogen group.
You're bouncing around the answer.
It's closest to the top right corner.
Which is, not quite the top right corner. The top right corner of the table that actually does stuff, right? Fluorine. So whichever one is closer to fluorine is going to be the one that's going to be more likely to grab electrons away from each other. So that the easy way to know that is the bromine is closer to fluorine. So it's gonna be the one that's more likely to gain electrons than the silicon is. And then as far as the number of electrons go, why is that the case? Why is it? Let me say this again. Looking at the table and saying, I know which one is going to react, is just telling me which one is going to react. Now tell me why bromine is the one that's going to react. No, that's how you know.
To gain an electron?
More specific.
That's as specific as I can get.
One. It needs to gain 1 electron. And silicon?
Like 3.
Count again. 4. It needs to lose 4 electrons or it needs to gain 4 electrons. So is it harder to get one thing or get 4 things?
It's hard to get for.
Hard to get 4. So is the silicon as good at getting electrons as the bromine? No. If you had like a set of something and you just needed one more thing to complete that set, you're going to be a little crazy about getting that last thing to complete the set. But if you still needed 4 out of 8, you're like, all right, I'll get it eventually. But so this is the bromine needing one more electron. So sulfite, polyatomic ion, electrons and protons. Which one of those should you do first?
The protons.
I'd do the protons first. So what's the formula for sulfite? That it?
-2.
Okay. So how do I add up the proton number? So 16 for the sulfur, 8 for the oxygen, so 24 and 16 gives us, and so there's my proton number, and then my electron number.
41. 39.
42.
Isn't it just one different?
Uh-uh,
Two.
it's 2. What does that -2 mean?
I thought that meant they like cancel each other out, but there's one difference.
No, that means that 2 haven't been canceled out. So whatever the charge number is, that's the exact number of differences between protons and electrons. So in this case, since the value is negative, then that means I have 2 extra electrons. That all 40 of the protons have been canceled out with 40 electrons, and I still have 2 more electrons not being canceled out. Does that make sense? So what would, tell me about that. Beryllium is atom number 4. So tell me what that consists of.
Missing 2 electrons.
So tell me exactly what's in this thing, this ion.
4 protons.
4 protons, because it has to, because it's beryllium,
2 electrons.
and 2 electrons. So it's just an indication of the disparity, the unequal nature of the fact that this is an ion, and so the sulfite has 2 extra electrons, and the beryllium here has 2 extra protons. And how do I get 2 extra protons? That's probably not the best way to say it. What should I really say?
Missing 2 electrons.
I'm missing 2 electrons, because you don't gain or lose protons. You have an X number of protons, and then I add or subtract electrons to that. So I wouldn't say that the beryllium gained 2 protons, because it didn't. It just lost 2 of the 4 electrons that it's supposed to have as an atom. Ion. So after that explanation, what's an ion?
Charged particle.
Okay. A charged particle. And what's the charge due to?
A different number of protons and electrons.
An uneven number of protons and electrons. That's it. Molecule.
Specific, like 2 or more atoms that are chemically bonded.
And their protons and their electrons are equal to each other. It is not a charged species. So ions have to have a charge, and the molecules are not allowed to have a charge. Cation?
Positively charged.
A positive ion. And then the anion? So cations have done what? Lost electrons. And the anions?
Yeah.
And you can't have one without the other. If I've lost electrons, it's not like the electron just shot itself into space and it's gone forever. It lost it because it gave it to something else. You get a cation because an anion was formed, and you get an anion formed because a cation was formed. Why is lithium happy to form a compound with bromine atom?
Because lithium wants to give away one, and bromine wants to gain one.
Exactly. So I've got lithium, and its Lewis dot structure is a single dot. So it's got one active electron ready to do something. And this is going crazy. Stop. I'm not even touching it. I'm nowhere near it. So the bromine is missing an electron right there, and that lithium is very, very happy to give it away. So we will definitely have a reaction happen as that lithium transfers that over. And then when that happens, what is this called? I'm sorry, I didn't mean the molecule. That is what it's called, the name. What is this process called? What kind of a reaction is this? The other one. Why is this an ionic bond?
Because they give electrons, not share.
Give, not share. Exactly. It gave those electrons over to that. That one electron actually left possession of the lithium, and now the bromine has possession of it. What's lithium's electron configuration before and after? So it's 1s2, 2s1, and then after it's lithium with a plus charge, 1s2. Huh, sorry about that, not giving you space there. I don't know how that happened. So for the bromine, it's 1s2, 2s2, 2p6, 3s2, 3p, yeah, 6, 4s2, 3d10, 4s, 4p5. There we go, 4p5. And so that P5 is the one spot that the electron is missing. So then when I switch this over, it's the only thing that's going to change is what? It's all of that's going to be the same, but it's going to be 4p6 instead. Oh, and the other thing is when I write this out, I'm going to write bromine with a negative charge next to it because it does have one extra electron. So don't forget to put that little thing there if you're drawing out the electron configuration. All right, how about a salt? What do you guys have for that?
It's, isn't it just an ionic bond between a metal and a non-metal?
It's just the common name for an ionic compound. And metal and nonmetals are ionic, but not all ionic bonds are metal nonmetals. So what's the actual definition? A cation plus an anion. And that will be a metal and a nonmetal, but it'll also be times when there isn't any metal there. How about salts? I'll just get the first one out of the way. What else we got? So from that definition that we just had, what else you got for a salt? Potassium chloride. Okay. How about something else?
Lithium chloride.
You guys are very boring. Magnesium sulfate. I have a very small amount of that in this thing right here. Does anybody know what magnesium sulfate is?
Isn't it Epsom salt?
It's Epsom salt. Yeah. Anything else? One more salt?
Potassium bromine.
Sure. So I just said that I've got some of this stuff in this water bottle here. Does this thing taste salty?
No,
Why not?
there's not enough of it in there.
No. If I put a quarter teaspoon of table salt into this, I'd taste table
Yeah.
salt. When you say something is salty, what should you really say?
There's a lot of salt in it.
No?
You can taste the salt.
What is it that you're tasting? Sodium. So when you taste something and it's salty, really you should be saying this is sodium-y. Because I could put an entire tablespoon of Epsom salt in your mouth, it would not taste salty. It'd be crunchy unless you generated a whole bunch of saliva, but in no way would it taste salty. So we continually say salty because the most common salt is table salt, but there are billions of combinations of things that make salt, and none of them taste like the things that you put on your fries. Only one thing would taste like your fries. What would that be? Any salt with what? Sodium. Sodium chloride, sodium bromide, sodium iodide, sodium anything is going to taste salty. Now, the other thing might be completely benign in your system, like chlorine or iodide, or it might kill you immediately. But at least it tasted salty right before you died. What you're tasting is the sodium. So when you think about something that's salty, you're really just getting a whole bunch of, specifically, what are you getting?
Sodium.
Nope.
Na ion.
Ion. This is what activates the saltiness inside of your taste bud. So is there any of that here?
No.
That's why Epsom salt doesn't taste salty, because it's the wrong kind of salt. Why are salts stable? What do I mean by that? Stable.
Like non-reactive.
Yeah, if you take table salt and throw it in the oven and crank the oven up to the temperature where it self-cleans, which is like 750 degrees Fahrenheit, does anything happen to the salt? No, it's just sitting there. If you took it and put it in the Bunsen burner, table salt, would anything happen? No. The melting point of it is 1700 degrees Celsius, and those Bunsen burners get to like 650 degrees Celsius. So nowhere even near close to the melting point. So why is it that they're not reactive? No, gasoline's neutrally charged. I wouldn't call that not reactive.
Because they already reacted like a ton of years ago.
They already reacted probably a gajillion years ago. So when you're talking about this table salt right here, what did it do bajillion years ago? One electron here went over there. And it happened a long time ago. And the reacting that sodium does is giving that electron away. And if it's already given that electron away, it doesn't do anything. So how about this Epsom salt? What has this Epsom salt done a long time ago? Okay, so specifically, what happened with the magnesium?
It gives some away.
It gave away 2 electrons a long time ago. That's what happened. I mean, maybe not. Maybe it was last week. I don't know. It doesn't matter. It could have happened at any point in history. It gave them away, and now all bets are off. It's done. Unless I shove energy back into it, that thing is pretty much said and done. Is that it?